All right, we're going to talk about the sum and difference formulas today, which are going to be new formulas. We haven't had new formulas for a while, and this is going to require a lot of proving, kind of like we did last section where you're proving one side equals the other. That's what we're going to be doing today, but we're going to be actually proving identities, such as the main question here is the sine A plus B the same thing as sine A plus sine B? Now, you should know the answer to that already, and that answer is no, because you're not multiplying, you're not going to distribute, it's a function. So the question is really, what is that answer? And this proof in this book is going to start the identities off, and then we're going to use the one identity to prove the other 5 identities today. So we're actually going to be looking at 6 total identities and their sum and difference. So we're going to look at sum and difference for sine, cosine, and tangent. You don't have to write anything down for this first proof, but what I wanted to show you how they're coming up with the sum of cosine, and it's all based off of this somewhat complicated diagram. You're going to see that in order to get cosines, the sum of cosines in a diagram, you're starting with angle A and adding to it angle B. And then when you get to that point, it's really going to be the cosine of A plus B. So that's how they introduce it into this diagram. And then when you go down here, this introduces a negative B into it. But the way this is set up is it's pretty complicated. It's saying because this angle right here, A, to negative B, is the same distance, the same angle as A plus B. So A plus B and A minus B is the same angle. And if that's true, that means that this chord is the same length as the chord from here to here. So this covers angle A plus B. This covers angle A plus B just in a different way. And then you're saying those distances are the same. And that's the whole basis of this proof, is saying those distances are the same. And then it goes on and on and on and on here in whittling it down to eventually getting this particular identity. Now, we're not going to go through this proof, but the main idea is just to set up and know that it's possible to derive this identity. All of the 6 identities today should be in your big rock sheet, so you can look at those as you go through the homework, and I will be providing those for you on the test. So what that means is we're going to take this identity and use it to prove the other 5 identities. And so let's go ahead and do that, and then what we're going to do is go through some problems using the identity. Now, a couple things that you need to know in order to do these proofs. One is a refresher on odd and even functions, and then cofunctions. So you have to know these details in order to understand the proofs of these sum and difference formulas. So the background information is going to be the fact that the sine of negative x is equal to a negative sine x. That's an odd function. And the cosine of negative x is equal to positive cosine x. That's an even function. Both of these are going to be utilized. I don't want to explain why that's true. We're just getting that information from what we've had before. The second idea that we're going to use is going to be the statement that says the trig function of an angle equals
cofunction of the complement of the angle. That's the phrase that you've said one day like 3 or 4 times, repeating it, and that's like saying, for example, the sine of theta is equal to the cofunction, the cosine of the complement of the angle. You may remember that, and we didn't do much with it back then, but we're using both of these concepts and proofs now to come up with the proofs. Again, you have to know this in order for the proofs to make sense, but these proofs are going to be a little bit tricky, and the reason why I prove things is so you can see where they come from and hopefully get a little bit better understanding. I'm also going to show you how I remember the identities as I go through. So we're going to use these concepts as we go through. Let's go to the identity that was shown in the book is this first one. Cosine of A plus B is equal to cosine A cosine B minus sine A sine B, and that's multiplication of these trig functions. The way I remember that is the cosines go together, the sines go together, and then because that's easy to make it hard, it's the opposite sign. S-I-G-N sign. So the positive becomes negative. Cosines minus sines breaks it down. And then the question is, if you know that that's true, which is that proof where it showed the chords are the same distance, if you know that's true, then how do you show that the second one is true? Well, the way you show the second one is true is you say, okay, I'm going to take this, I'm going to say cosine of A plus a negative B. That's the same thing as what's above it. And so what I'm really doing is I'm just substituting in negative B in for my positive B. It's a direct substitution. So this is given, this first identity. And so I just want to put in negative B where the positive B is on the second one. So this becomes cosine A cosine negative B minus sine A sine negative B. Because my second one, my second angle is now negative B, not positive B. All right, so now how do I simplify that? This gets into the odd even functions. This becomes cosine B, and this becomes actually a negative sine B, which means if you bring that negative out front, it turns that into a positive. So that's why it's plus sine A sine B. And this is the same identity as this. So all we're applying to get from the first one to the second one is the odd and even functions with that negative B. 2 out of the 6 are done. You're going to have to hang with me today because this proving can get a little bit tedious. The next one is going to be, what about the sine, sum, and difference formulas? Sum because A plus B, difference because of A minus B. So the sine of A plus B is equal to sine A cosine B plus cosine A sine B. How do I remember this? I remember with the sine, it's the mix of the two. And because you're mixing it here, it's a little bit more complicated. They give you a break on the plus sign, which is the same, or the minus sign, which is the same. So you mix the two, and then use the same exact plus or minus. Well, how do I prove that the sine of A plus B is equal to that? The way that I prove that is actually with the idea that back to the first slide, the trig function of an angle equals the cofunction of the complement of the angle. So I'm going to use that to switch it from sine to cosine, and then I can apply my previous identity. So the sine of a plus b equals the cofunction, the cosine of the complement of the angle. Cofunction of the complement of the angle. That's just for starters. And then what I have to do is I'm going to rearrange this so I can do an identity here for the cosine, but the way it's written right now is not going to work because I need to separate the a and the b. I don't want that a and the b to be together, or else it's not going to give me my identity. So the way I'm just going to separate that is going to be 90 minus a is my first angle, and then my second angle is going to be minus b. In other words, I distributed the negative through, and then I grouped the 90 minus a and the b together. So it's just rearranging those to now angles being in different parts. All right. Now I'm going to apply the cosine identity, which is a difference, cosine difference identity, which I have from before. So that means I'm going to rewrite the whole thing now. Cosine 90 minus a times cosine b plus sine 90 minus a sine b. Okay, so I have the cosine plus sine, sine. At this point, I want to simplify it. And I'm going to again use that same principle that the cofunction of it, the function of an angle equals the cofunction of the complement. But look what I have here, cosine of this angle. Well, what's the complement of 90 minus a? The complement of 90 minus a I can do out here. 90 minus 90 minus a is the complement. Well, what happens? 90 minus 90 is 0. You just end up with a. Kind of makes sense. A and 90 minus a are complements. So the cofunction of the complement of this is just sine of a times cosine of b plus, again, cofunction of the complement, cosine of a times sine of b, and you just showed why it's equal to the right side. That's what the c is. Then, so that's the main idea on that cofunction property. Then the question is, well, how do you get from c to d? It's the same business as before, odd and even functions. So if you put in a negative b for cosine, this just becomes cosine b, which is the same exact thing. If you put in a negative b for the b and the sine, what happens? This becomes negative sine b. The negative comes out front, and you're left with minus that term. So that's pretty easy to prove after you get the first one, proving the second one. Same idea as what we did before. That takes care of 4 identities. We've got 2 more to go, which are the tangent identities. So we have a tangent a plus b and then a tangent a minus b. And we're going to do the same thing. We're going to prove one and then just use the odd and even functions to get the other one. The tangent is actually an odd function. And tangent is odd means tangent of negative a is equal to a negative tangent of a, just like the sine being odd as well. All right, so how do we go ahead and prove this? What you're looking at is if the tangent is odd, I'm going to go ahead and start with the left side because I don't know what tangent of a plus b is, but I know what the sine of a plus b is, and I know what the cosine of a plus b is, so that's how I can break it down and simplify. So so this is how I'm going to do it. Tangent of A plus B equals sine of A plus B over the cosine of A plus B. Sine over cosine. That's the ratio identity. So now what I want to do is actually expand the top and the bottom. The sine of A plus B I learned, the cosine of A plus B I learned. I just want to substitute those identities in. So I'm going to say this is equal to sine A cosine B, cosine A sine B on the first one, over, and then it's going to be cosine A cosine B minus sine A sine B. Again, those are from the previous slides that we developed. Now, the only thing that I need now is to recognize that this term right here has got to be equal to 1 in order for this identity to equal the right side. If I know that this is equal to 1, then how do I go from this term right here to 1? I just have to divide that by the same term. If I divide it by the same term, I do get 1. So that's what I want to do to the top and the bottom. I actually want to multiply both the top and the bottom by the reciprocal of this term. So this looks a little complicated, but it cleans up real nice. 1 over cosine A cosine B over 1 over cosine A cosine B. That's still equal to 1. But now when I distribute it through, you're going to see that I'm going to get the right-hand side of that. So first of all, let's go to the bottom. That's a little bit easier. If I take this term and start distributing this through, 1 over this times this is the same thing as 1. They're going to cancel, so you're left with 1 on the bottom. Minus, start over, go to the second term. Notice what happens here. The sine A over cosine A is tangent A, and the sine B over cosine B is tangent B. Looking at the top one, cosine B's cancel. I'm left with sine A over cosine A. Sine A over cosine A is just tangent A. Start over, going here. What happens? The cosine A's cancel. I'm left with sine B over cosine B, which means plus tangent B. That gives me the same identity as E, which means now you've got basically the proof for all of them, because to get from this one, E, to F, all you're doing is substituting in negative B for your B, and it's an odd function, so that's why it's minus tangent B, and that's why this sign changes, because you get a negative tangent B, and then it switches with the negative sign, and now you got this function. So we've got all 6 functions with a general idea of where they came from. Let's go ahead and apply those identities to the next problems. So we're taking all of the identities now, 6 identities, and we're just going to do some problems with them. And what I'm going to do is, the first question is, what is the cosine of 75 degrees? Cosine of 75 degrees, what we're going to do is, what is the exact value of the cosine 75? And that means you want radicals in it. I don't want to use my calculator. I want to change that to a sum or difference equation or identity, and then solve. Cosine 45 is the same exact thing as cosine 45 plus 30. Why do I pick 45 and 30? Because I know what those are from my table. I then use the identity to expand it. And so this becomes cosine 45, cosine 30 minus sine 45 sine 30. Strictly using the identity. Then I go to my table and pull up those values. So I know cosine of 45 is radical 2 over 2. Cosine of 30 is radical 3 over 2. Notice it makes a difference which form I put that cosine 45 in, because now I can simplify it easier if I choose the right form. Sine 45 is going to be radical 2 over 2, and the sine of 30 is equal to 1/2. How do you simplify? Radical 6 over 4 minus radical 2 over 4. You leave it in that form. There's no reason to simplify it anymore. There are no radicals in the denominator, and that's fine. Similarly, we're going to do the same idea for the next example. It says show cosine x plus 2 pi equals cosine x. X plus 2 pi, remember that means just going around the circle one time. So when you go around that circle one time, you should end up with the same value. It's just we haven't really said the reason or proved it. It's just on the unit circle, you can see it goes around or in standard position. But how can we prove it with an identity? I can prove it by using the sum of cosines. Sum of cosines is going to be cosine x cosine 2 pi minus sine x sine 2 pi. Simply substituting them in, and now I want to evaluate. To evaluate, you can see that you can get both of those answers as numbers, and therefore you can simplify. Well, what do you get? Cosine 2 pi. What I want to do is draw the cosine value, and I also want to draw the sine graph. So this becomes like that. The reason why I'm doing that is because I want to pick off those points. Well, what are those points? Let's see. Cosine of 2 pi is going to be right here. Therefore, that's equal to 1. Cosine x times 1 minus sine x, sine of 2 pi. Sine of 2 pi is right here. That is equal to your y value of 0, which means that this is going to be times 0. That becomes 0. You're just left with cosine x equals cosine x at this point. So you're able to prove that if you're adding or subtracting pi times 2 or 2 pi, you get the same value. This next problem looks complicated, but it's not. It says it's cosine 3x cosine 2x minus sine 3x sine 2x, and you're supposed to write this as a single cosine. The only thing you're really doing here is you're recognizing a pattern, and you're going from the right side to the left instead of the left to the right. And the pattern is where you have cosine A cosine B minus sine A sine B. So if I go back to my identities, you're going to see that it's going to be right here, where it's cosine A cosine B minus sine A sine B is cosine A plus B. Cosine A plus B, that's all I have to remember. Cosine A plus B, cosine, my A is 3x, my B is 2x, so it's just going to be cosine A plus B, which means it's just cosine 5x and you're done. Those problems, again, look hard, they're easy. They don't take much time at all. This one is just like the other one. It says, show the 90 minus A equals the sine of A. I'm just going to substitute in the values and then move on to the next problem. But it's the difference of cosine, so it's going to be the cosine 90 cosine A plus sine of 90 sine of A, and then you would just put in the values and show that it's equal to sine A. Don't want to spend much more time on that one. Very similar to what we did before. Notice you can do it in degrees, you can do it in radians, it's all the same idea. Two more problems. What is the exact value for the sine of pi over 12? That creates a little bit further challenge because you're dealing with pi over 12 instead of degrees. And so you got to remember your special angles for radians. So what I want to do is I want to list these special angles so I know what I'm looking at. So I'm at 0, pi over 6, pi over 4, pi over 3, and pi over 2. And I want to somehow be able to figure out how I can get pi over 12 by either an addition or subtraction of these values. Again, putting it on paper helps me figure out what it looks like. What do I have to do? To help me even further, if I can get a denominator of 12, it'll be even easier yet. 2 pi over 12, 3 pi over 12, 4 pi over 12, 6 pi over 12. I'm converting them all to the same denominator just so I can figure out how to get pi over 12 when I look at this. At this point, you could pick either one. You could say, well, 3 pi over 12 minus 2 pi over 12 works, or 4 pi over 12 minus 3 pi over 12 works. Either one of those is perfectly fine, but you want to rewrite it as one of those. Let's just do 4 pi over 12 minus 3 pi over 12. And let me warn you that sometimes in the back of the book, the answers may be different, but they equal the same exact thing. So you have to be careful about saying if your answer is right or not. I plug it into the formula, sine, and I can say, I can use these, or I could use, this is probably easier just to say it's pi over 3 minus pi over 4 now. So this is sine pi over 3 times cosine of your b, which is pi over 4, minus cosine pi over 3 sine pi over 4. It's using the sine and cosine in different ways. Then you would go to your table and get values off. So this becomes, let's see, sine of pi over 3 is 1/2. Radical 2 over 2 minus, let's see, no, cosine of pi over 3 is radical 3 over 2. Cosine of pi over 3 is equal to 1/2 times radical 2 over 2. This becomes radical 6 minus radical 2 all over 4. Nothing you can do to really simplify that. All right. So we have one more problem, which is going to be using tangents. We haven't done a problem with tangents. So this is going to be tangent 75. Same idea as before. I want to break up the 75 in terms of special angles so I can evaluate. I want to either use a sum or a difference. 75 you've seen before. I would just do tangent of 45 plus 30. some formula for tangent. I'm now going to plug in. You're going to need a lot of space for this one because once you get going on this, you'll see simplifying the fraction becomes the main problem of this. Tangent. This is your A, this is your B, so it's going to be tangent A plus tangent B over 1 minus tangent A tangent B. Direct substitution into the identity. Well, the good news is that the tangent 45 is equal to 1. So I can help myself out quite a bit by just replacing 1 with the tangent 45. Tangent 30 is 1 over radical 3. So I now need to rewrite that. 1 plus 1 over radical 3 over 1 minus 1 over radical 3. Well, you've got a couple problems here. I mean, technically that's right. It's just not simplified. And so to simplify this, you got to get the fractions out of fractions, and you have to get the radical out of the bottom. So now it becomes a big algebra problem. First thing I want to do is wipe out those radical 3's. We've done that in the last section by multiplying through by the common denominator, which is radical 3 on the top and radical 3 on the bottom. So this becomes now radical 3 plus 1 over radical 3 minus 1 when you distribute through. And you can also get rid of the radical on the bottom by multiplying something called the conjugate. And the conjugate is really radical 3 plus 1 on the top and the bottom. It's the opposite sign as that, negative, and you will see that when you do that, you actually get 4 multiplications on the top. So I'm just going to distribute that radical 3 through. It becomes radical 9, which is 3, becomes plus radical 3. Then it's plus radical 3 plus 1. The bottom, you make an observation that the inner term and outer term cancel. Radical 3 negative, radical 3 positive becomes 0. So really you're talking about the multiplication of the first two, the first and the last. So it's going to be radical 3 times radical 3 is 3, and then negative 1 times 1 is going to be negative 1. At this point, you simplify 4 plus 2 square roots of 3 all over 2, and that can be written as 2 fractions, 2 plus radical 3. And you're done simplifying at that point. So there's a lot of algebra at the end of this, and it simplifies to this. Be aware, answers are going to be different. Sometimes in the back of the book, you have a lot of radical situations. Check by using your calculator. And I'd also make sure you have those identities clearly written in your big rocks so you can write down your problems correctly.